Welcome, everybody. It's my pleasure to introduce Facundo Mémoli, and today he'll be telling us about Vietoris-Rips persistent homology, injective metric spaces, and the filling radius. Thanks, Facundo.
Thank you, Henry. So I'll switch to the screen. All right. So I wanted to describe some recent work with Sanyuk Lim and Osman Okutan on relating persistent homology to the notion of the filling radius. So just a quick review of the Vietoris-Rips filtration. I mean, possibly everyone is already quite familiar with this. So all I will say is that I'm using the open condition here, and I will denote by bark asterisk the collection of all barcodes that you obtain from the persistent homology of this simplicial filtration. And the asterisk refers to the fact that I'm stacking the barcodes that I get for all degrees. The Vietoris-Rips filtration has been used for many, many years, maybe 20, 30 years in computational topology. And it was only recently that, I mean, a lot of effort was done by Adams and Adamaszek was put into characterizing the barcodes for the circle with geodesic distance. And what was also done was to notice that the successive homotopy types of the epsilon Vietoris-Rips complexes touch upon S1, S3, S5, S7, all odd dimensional spheres. So, and other things that I wanted to point out, there's a software nowadays that computes barcodes for the Vietoris-Rips filtration quite efficiently. I suggest having a look at Ripser if you haven't already played with that. It's also known that as a map from compact metric spaces into barcodes, into the collection of barcodes, the Vietoris-Rips barcodes are two Lipschitz under Gromov-Hausdorff. And in practice, Vietoris-Rips barcodes are used for classification tasks. So let me now describe three motivating questions for the research related to this paper. One of them is the following question: how strong are these Vietoris-Rips barcodes as invariants of compact metric spaces? So namely, suppose that you have two compact metric spaces with the same barcodes. Does that allow you to conclude that the spaces are isometric, homotopy equivalent, whatever, right? So in general, the question is, I mean, there are some non-too optimistic examples. For example, you can consider S1 with, say, the geodesic distance. And then you can consider a copy of S1 to which you attach a lot of trees. It can be proved that these two metric spaces actually have the same barcodes for all dimensions. But of course, by taking these branches to be as long as you want, you can make the Gromov-Hausdorff distance between them to be very, very large. So one thing that is suggested by this example is that we should maybe contemplate asking this question in the manifold case first, so that we don't have these strange junction points. I should mention that the verification that these two barcodes agree was done by Osman Okutan in his dissertation. Second question is how can we relate the length or the endpoints of Vietoris-Rips barcodes to other geometric invariants of a compact metric space. Of course, we can always say that the depth time of any interval in the barcode is bounded by diameter, but this is rather coarse, and we would like to substitute this by other more sensitive invariants. And another question, the say bigger question, is how to characterize the successive homotopy types that are attained in the Vietoris-Rips filtration of, say, spheres with possibly different metrics. We could be talking about the geodesic metric, or maybe it's the L infinity metric, the L2 metric, etc. And of course, beyond spheres, we are also interested as a community in other canonical spaces like tori, etc. And I already mentioned the work done by Adams and Adamaszek about the complete characterization of the successive homotopy types of Vietoris-Rips of the circle with geodesic distance. I want to now jump directly into the definition of a filling radius. So for that, I first have to remind you of the so-called Kuratovsky isometric embedding. So if you're given a compact metric space X, then consider a map K that goes from X into L infinity of X. And I view L infinity of X as a metric space by considering the infinity norm, the supremum norm between functions on X. So you send every point X in X into the distance function to that point. So L infinity is a collection of functions on X, and this is a function associated to this given point. It's not difficult to prove that this is actually an isometric embedding. So you have this relationship here. Now, if you start from X via the map K, you embed X isometrically into L infinity of X. And in particular, once you are in L infinity of X, you can think that this is X. And of course, you can consider epsilon thickenings for any positive epsilon of X inside of L infinity. So that gives you this map, the inclusion map, iota epsilon from X into its epsilon thickening. So at any rate, so I will use this notation here. I will write X epsilon as the open ball of radius epsilon around X in L infinity as an ambient space. And that's what I will call the epsilon thickening of X. So if you're given an n-dimensional closed Riemannian manifold M, and let me assume that M is orientable. So then this map, iota epsilon from M into M epsilon, induces a map on top homology. So iota epsilon from HNM into HN of M epsilon. And Gromov considered the infimal epsilon for which this map kills a fundamental class of the manifold. And that's the filling radius of M. So in a sense, filling radius tells us how robust is a fundamental class under the inclusion into epsilon thickenings. So this suggests that at least at the philosophical level, there should be a connection with persistence. So the filling radius, apparently first appeared in a paper written by Gromov in the 80s, paper called Filling Riemannian Manifolds. And one of the, theorems in that paper is the following systolic inequality. So if you have an n-dimensional closed aspherical Riemannian manifold M, Gromov proved that the systole of M, that is the length of the shortest non-contractible loop in M, you can think of a torus, and that would be the systole, the length of that loop. The theorem states that the systole of M is bounded by the 1 over n, the nth root of the volume of M times some universal constant. And the filling radius appeared in the proof of this claim. So first, Gromov proved that the systole is bounded by 6 times the filling radius. And he pointed out that this step is actually true for aspherical manifolds. But then he also calculated that the filling radius of M is bounded in this way by the volume, and this is true in general for any manifold. And then by combining these two steps, you can actually attain a proof of the theorem. I should mention that this part here is actually not difficult to prove, whereas this one, there was a lot of subsequent work in trying to clarify the proof and provide like simpler proofs. So the definition of the filling radius suggests considering what we could call the Kuratovsky filtration. So given a compact metric space X, one can consider the collection of nested open balls around X. So this will be the X epsilons X epsilon prime and an inclusion between them. Notice that, of course, we could do the same, not just for L infinity of X, but actually for any ambient space E, inside of which you can find an isometric embedding of X. So keep this in mind, please, because it will come up later on. But at any rate, here it's the Kuratovsky filtration refers to this construction when E is L infinity of X. So we proved an isomorphism theorem taking the following shape. If you consider the Kuratovsky filtration here, so you have X epsilon and an inclusion into X epsilon prime, and then down here, if you consider the geometric realization of Vietoris-Rips with 2 epsilon for X, Vietoris-Rips with parameter 2 epsilon prime for X, and this is a map induced by inclusion at the simplicial level, then there exist homotopy equivalences, phi epsilon prime, that make this diagram commute up to homotopy. And one useful remark is that the theorem is true not just for the construction of X epsilon via L infinity, but also for a construction of X epsilon for any ambient space E, which admits an isometric copy of X. And furthermore, and this is important condition, E is required to be injective. And I will explain what injective means in a few minutes. So some immediate consequences are, well, first of all, because of this commutativity up to homotopy, if you apply homology, then you're going to have that the persistent module induced by the top line and the one induced by this row will be isomorphic.
And Facundo, I think Giannis has a question. Giannis, please go ahead.
Yes, thanks. I just put it in the chat. I was wondering, is there some intuition for what this map phi does? Like I got, or I think I got the previous way where you embed into infinity, but this, I'm not sure what to be thinking of.
I can explain that. Let me delay answering that question until the end, but yes, I'm prepared to provide you with at least some intuition for that.
Okay, thanks.
So then a consequence is that these two filtrations have isomorphic persistence. And in particular, what that means is that now we have some sort of a bridge between applied algebraic topology, which has mostly been thinking about this one, and then results in Riemannian geometry that have, through the notion of filling radius, been thinking about this other filtration. So the first one is that if you look at an n-dimensional Riemannian manifold M, and then you look at the barcode in degree n of M, then there's always a special bar there. And that's a bar starting at 0 and dying at twice the filling radius of M. And that is a bar corresponding to the fundamental class of manifold. And we called it I and M. So one interesting thing is that now that you know that you always have this bar for any compact, say, Riemannian manifold, blah, blah, so you know also how to relate the length of that, and say the depth time of that bar to the volume of the manifold. And this comes immediately because of the one of the steps in, the conclusion of, one of the steps in the proof of the systolic inequality that I showed before. So I need to jump back here. Right, because of this step, you can conclude that your special bar has length bounded by volume. So in a way, if you were able to approximate or compute the barcodes of a manifold, and you see a bar in 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 the n degree n barcode, which is sufficiently long, that means that the volume of the manifold is also forced to be not too small. I mean, it was surprising to me that we could say that with barcodes, but anyway. So this is going to be the notation that I use for later. Something else that we can import is work done by Katz in the 80s related to the exact computation of the filling radius of spheres. As I mentioned at the beginning, we don't yet have a lot of information about Vietoris-Rips barcodes of spheres. We know perfectly well what is a Vietoris-Rips barcode for S1, but for a general N, things become much more complicated. So via the previous, the result in the previous slide, and via calculations done by CATS that yield a precise value for the filling radius, we now know that this bar is always in the barcode of Sn. So let me say what this number is. So CATS proved that the filling radius of Sn is 1/2 of the side length of a geodesic, a regular geodesic simplex inscribed into Sn. So, for example, for n equals to 1, you have 3 points, and our cosine of -1/2 is 2 pi over 3. So which coincides with the number computed by Henry and Adamaszek. Then for S2, well, the number is going to be more complicated. I don't have an easy expression for a cosine of -1/3, but that gives you an idea of what's happening with this new bar, say. And yeah, so it's also useful to know that all the bars have length at least pi over 2, which follows by looking at that expression. Some other immediate consequences are QNet formulas and formulas for the persistent homology of metric gluings. These happen to be a little bit simpler to prove in the context of Kuratovsky filtrations as opposed to directly trying to prove them at the simplicial level. I mean, I don't have the time to explain why that is the case, but there has been a lot of work in recent years into trying to prove, formulas for both metric gluings and the products. And I should say, yes, I mean, we can do something more easily in the setting of L-infinity products of metric spaces. So we're using the max to combine metrics on X and Y. Perhaps, the more interesting consequence is the following: is some rigidity result for spheres. And this one followed directly from work done by Wilhelm in the 90s. And in a nutshell, the claim is that spheres are fully characterized by their Vietoris-Rips barcodes inside the class of manifolds with curvature bounded below by some positive constant. So here is a statement. Fix some number n, natural, then there exists an epsilon n positive such that whenever M is an n-dimensional closed connector Riemannian manifold with sectional curvature bounded below by 1 uniformly, then you have the following consequences. The depth time of this special bar will be bounded by the depth time corresponding to the n-dimensional sphere. Equality between depth times forces M to be isometric to Sn. If dn is smaller than dsn, but not too small, then M has to be diffeomorphic to Sn. And then if dn is at least pi over 3, then it's homotopy equivalent to Sn. This is a relatively, say, good news for for barcodes, in the sense at least we have one case in which we know the barcodes are strong enough to detect a particular geometry. And this should be compared to the Bonnet-Myers and Cheng's sphere rigidity theorems. In analogy to this theorem, Bonnet-Myers tells us that the diameter of M has to be bounded by the diameter of Sn, and that this is Bonnet-Myers, and then Cheng tells us that equality implies isometry. So that would be, say, the genesis of this type of theorems. Right, and this is just a pictorial representation of what happens in different ranges of the N. All right, so I already mentioned these two items here. I also wanted to say that Katz did a lot of work, not just in the context of spheres. He also considered CPN, and he has some understanding of homotopy types that, for the case of S1, Katz did via Kuratovsky type of ideas, some calculations that led him to prove that the second homotopy type attained by Vietoris-Rips, well, say by Kuratovsky thickenings of S1 was actually S3. And this is what I wanted to mention is that the bridge given by the Isomorphism Theorem provides a complete answer to some questions that Katz had, namely in the shape of the work of Adams and Adamaszek. All right, so as I mentioned, we still have no complete picture about the general question related to the successive homotopy types of Sn. But that also led us to ask the following question. Suppose that I metrize Sn not with L2 metric, not with geodesic distance, but with the L infinity metric. So what I mean by that is take any embedding, well, say take the usual embedding of Sn into Rn+1, the round sphere, and give to the round sphere the restriction of the L infinity metric in ambient space. So it turned out, surprisingly, that in that case, you have a very tame situation, namely, instead of a infinitely many different homotopy types, like in the case of Sn, say S1 with geodesic distance, we have only two. So the Vietoris-Rips complex of Sn with the L infinity metric behaves like Sn for epsilon in that range, and after that becomes contractible. So how did we prove this? Well, here's one idea. So as I mentioned before, our isomorphism theorem holds true not just in the setting when you define thickenings to be those that take place in L infinity, but the theorem holds true when you choose any other ambient space E, which is injective. And let me quickly explain what injective means. So a metric space E is injective if whenever you pick some other metric space and you pick a non-empty subset A of that metric space and you have a one Lipschitz map into E, then you also find an extension of that map from Z into E. Rn with the L infinity metric is injective. L infinity with the supremum norm is also injective. Metric trees are injective, for example. And there's an interesting phenomenon too, which is given any compact metric space X, there exists an optimal injective ambient space for X. And that is called the tight span and is denoted by E of X. E of X, the tight span of X, is defined to be the minimal injective space inside which you can isometrically embed X. The notion was discovered at least two different times, one by Isabel in the 60s and then by Andreas Dress in the 80s. And it satisfies some useful, say, efficiency type of properties. The diameter of the tight span is equal to the diameter of X. So the hyperbolicity of the tight span is equal to the hyperbolicity of X for a geodesic space. And then the tight span is always a geodesic compact contractible. The assignment from X to E of X as a map of metric spaces is also stable in Gromov-Hausdorff sense. Actually, it's actually two Lipschitz. And then if you ask yourself, I have X, and then I have the tight span of X, some bigger space. So then what is the distance between X and the tight span? You can prove that that distance, the Hausdorff distance in the ambient space EX, is bounded by hyperbolicity. All of these properties induce some interesting consequences. So back to the proof, I was trying to give some hint, some basic idea on how we prove that Sn has only two different homotopy types. In the Vietoris-Rips of Sn with L infinity attains only two different homotopy types.
Can I ask another question?
Yeah.
Sorry to keep breaking you up. Could you go back to the previous slide?
Mm-hmm.
What does it mean to be minimal among injective spaces? Does that does that refer to the extension condition?
It means under inclusion. Sorry, under isometric embedding. Yeah.
Okay.
Yeah.
Okay. Okay. Thank you.
No worries. All right. So back to the proof. We can in the isomorphism theorem, we can choose that to be E. As I mentioned before, well, first of all, Sn infinity is realized as a subset of this particular choice of E. And then, as I said before, Rn's with the infinity metric, the infinity norm, are actually injective. So this is a possible choice in the isomorphism theorem. So that leads to the conclusion that the neighborhood filtration is naturally isomorphic to Vietoris-Rips with twice a parameter. So then if you try to analyze this filtration, you will have to think of the thickenings under L infinity of, say, the circle. And you can do that by hand, and you can actually prove that the thickenings look like this. So it will be, thickenings will be homotopy equivalent to the disk. I can cut something out, minus some region in the center, which you can control fairly easily. This region is the intersection of some number of epsilon balls that are centered in the vertices of a hypersquare. How am I doing with time? So I'll finish in about 10 minutes. Let me skip this. Another thing that can be done at the level of Kuratovsky embeddings is to prove the surjectivity from pi1 of x into pi1 of Vietoris-Rips of x epsilon. I think, Henry actually mentioned this to me recently, that Shiga Berg did prove this result directly at the level of simplicial complexes. And we have a proof, or it is possible to give a proof at the level of Kuratovsky embeddings, which seems to be fairly succinct, indirect. So the there's an archive preprint with most of the things that I mentioned today, and thank you. I think I had a question.
Do you mean the question from Giannis earlier about the phi maps, or?
Yes, right. So that was the question, right? So what is the nature of the maps, or maybe I can interpret that more generally, like how do you even prove that theorem, right? Am I correct? Yeah.
Yes.
So the first observation. My pencil is not working. Let me see. Oh. That's strange that the pencil. Sorry, I'm having the Apple Pencil is not syncing.
No worries. Let me interrupt while Facundo's playing with this, and before we get to questions. So let's all briefly unmute ourselves and applaud for Facundo, and then we'll go into questions afterwards. So thanks, Facundo, for this very nice talk so far.
So strange.
Is it upside down?
Say that again?
Is it upside down, your pencil?
No. Not sure it isn't. Oh, there you go. It's working now. Okay. All right. So there are two different things to be done. First of all, that x epsilon is isomorphic to the check of x inside the ambient space. And the second step is to prove that this is isomorphic to, let me put 2 epsilon of X. This is when you use the injectivity of the ambient space. And for that step is where you have the nerve theorem. So the isomorphism theorem requires you to come up with a factorial factorial versions of that.
Facundo?
Yes.
So how does the nerve theorem give you an isomorphism? So this is usually it only gives you a homotopy equivalence as well, right? Is there something stronger here, or?
No, we don't. I didn't say. Did I say isomorphism? Sorry, yeah. I don't know if I use that word. No. So, okay, I'm answering the question about the homotopy equivalence. Sorry, I might have been translating
so both are
my
homotopy
head.
equivalences.
Yes. Yes.
Okay. Yeah. Okay.
And this one is actually an equality. This is equality as simplicial complex.
Yeah. Okay. Yeah.
Thank you. So the maps that you're referring to, Yanis, are the ones that appear at the level of the nerve theorem.
Okay. Thanks.
So the proof had to actually go directly to the guts of the nerve theorem and check that the maps in the usual proof that we find in Hatcher work factorially. Yeah.
Further questions for Facundo?
I had maybe a bit of a silly question. You had the barcodes you wrote were open closed, but I thought that they should be closed open. What am I confused? Why did you write them like this?
There one. Let's see where did I write them. Possibly relate this one.
Where? Yeah, for example, this fundamental barcode, like, because in 0 it just lives, right? Or
well, I'm using the open condition, so right. So if I put 0 there, it might be a convention, but right. So if I'm using the open convention for Vietoris-Rips, so what does it mean to put 0 here?
Right. Yes. I see. Yeah.
Yeah, I think it's simply because of that.
Yeah. I think I usually have smaller equal than yeah. Okay.
Yeah.
Thanks.
I have just a small question. So at some moment you introduced the notion of spread. Was that a notion that was introduced in the older literature, or is that you introduced and your coworker introduced?
No, that was present in the work by Katz.
I see.
And that is a. I don't know if it was somehow present in some other. In general, I presume no, but yeah. So the result is known for compact metric spaces.
And one other question is that for the epsilon thickening of circle or Sn in their injective envelope, do you have any intuition into that? What is the epsilon thickening for, let's say, S1 in its injective envelope?
So we don't have a precise description of that, but we know, say, what follows from the isomorphism theorem, that the homotopy type that you get for that injective space is the same as the one that you would get for any other injective space.
So for S1, at least for every compact space, we know something about the endpoints of their injective envelope. Let's say for S1, all points in S1 are endpoints. That means that you have at least one path that you cannot somehow extend beside these points on S1. And it means that somehow when you go to the injective envelope, these are the boundary kind of points in injective envelope. So if you take the epsilon thickening of this one, you are somehow coming inside the injective envelope.
I'm sorry, I didn't fully understand.
So let's say consider S1 in its injective envelope.
Yes.
You have this property of endpoints as discussed in the work of Isbell, that for each compact metric space you can consider the set of endpoints. These are the points that there is at least one point on the metric space that is that you have a path from that point to this specific point, and you cannot extend it beyond this point. So on S1, each point of S1 can be an endpoint. Because you can take the antipodal point and you cannot extend this path from the antipodal point to this one to beyond this point.
Yeah.
And there is a result that endpoints of the injective envelope are among these endpoints of the metric space itself. And for the case of S1, E of S1 doesn't have any other endpoint other than this one. So the whole space S1 is the set of endpoints in E of S1.
Yeah, I see.
And so if you look at it, you can see some kind of this disk inside A of X, and you cannot go beyond that. You can thicken it, but you cannot go beyond that. What would be the epsilon neighborhood or epsilon thickening of S1 in such a situation? This is somehow like something like cubical neighborhood around this S1 in this space. And so how you are going to maybe realize the homotopy? This is I think this is a very nice example in this situation. At least you have some intuition about it. What would happen here?
Right. So I totally agree. Yeah. So well, let me say that some small attempt at that was this here. Right. So in the case of S1 with the L infinity metric now, not with a geodesic distance. So we know this embeds into R2. But is Anyuk in the audience right now, by the way? Well,
yes, I'm here.
Yeah. So please remind me, what is the name of the authors of the paper that proved that the tight span of subsets of R2 infinity, you know.
Kulik and Kochak.
Kulik and Kochak. Thank you. Yeah. So in a recent paper, I think in Advances, Kulik and Kochak proved some results that imply that the tight span of S1 with the L infinity metric is actually the disk with the L infinity metric, which is a realization of, I think, what you were saying, Parvane, right?
Yeah.
So you can take S1, and then you know the disk is a model for the tight span. So, but then the interesting thing is taking the thickenings, and taking the thickenings here means, well, you have to take thickenings in L infinity sense, and that's what gives you these weird, shapes. See what I mean? Like you have to enlarge, and you may see that there are some lines here. These are actually because we tracked all the squares that you have to place around S1.
Yeah.
And as you increase epsilon, you're eating more of the interior of the disk until everything disappears at the same time. So there are no holes created ever. Also, something interesting is that the results by Kulik and Kochak are very tightly related to R2. They are not true in general. So it is not true that if you take S2 with L infinity metric into R3, it's not true that the tight span, well, at least we don't know if it is true, but it's not implied by this result. It's not necessarily true that the tight span of that is equal to the ball, the unit ball in R3 with L infinity metric.
Just in dimension 1.
So far, only in dimension 1.
Yeah, thank you.
I mean, no worries. Yeah. So Ling Chao is actually working on this. Ling is a PhD student at Ohio State, and she's been concerned with, interested with exactly the extension into S2, S3, etc. So, but at any rate, so by deflecting this slightly, it is possible to still analyze the homotopy types of the thickenings of Sn infinity into R1 infinity, and conclude that no matter what, you still have a two different homotopy types only.
Yeah, thank you.
Sure.
Ulrich, I think you have a question.
Yeah, now I have two questions. So the first one is, I mean, to me, it looks like it would be more natural to, instead of considering the Euclidean sphere, but then equipped with the modified infinity metric, to instead consider the boundary of the L infinity ball already in L infinity, right? Which is a different, and I mean, of course, yeah, I guess it's genuinely different metrically. So right, you take this Euclidean sphere, but then the infinity distance, somehow you're mixing up two things, and I mean, for me, it would sound more natural to instead consider infinity balls, which would be hypercubes, right?
Yes. So we do have some results, and I think I didn't write them into the presentation, but
yeah, okay.
That's something we did consider. And
okay.
Sorry, I didn't prepare for this slide, but I mean, I think Sanyu, please correct me, but I think the claim that we have in that case is that if you look at the nth L infinity sphere, then the thickenings also satisfy. Well, I'm sorry, so the homotopy types of Vietoris-Rips satisfy something very similar, but now the threshold doesn't depend on dimension anymore, which is something to be expected, right? Because
and I mean, here some of the question feels more natural than the other one.
Yeah,
and also
absolutely.
Okay, cool.
Yeah. So the reason for
go on.
Go ahead, please.
No, I wanted to move to, but you wanted to add something, and I wanted to move to the second question. So
okay, the reason for considering the round sphere in Sn is more like an intermediate step, right? For some reason, well, I mean, I think it might be actually related to what is easy to do in practice. If you have a point cloud, it's very fast to calculate the L2 distance matrix associated to that point cloud.
Yeah.
Simply because of the inner product property, right? But you can do everything in matrix as matrices, say in MATLAB. But the L infinity metric may be a little bit more expensive to compute. So it might be that for historical reasons, we always were computing things with L2 metric, and that led to questions about the L2 metric in the continuous setting. And as a consequence, also geodesic distance in the continuous setting. But I wanted to mention something I forgot to say before, that I recently came across a paper there's a paper actually where the authors are thinking of point clouds and then the impact of persistent homology on point clouds in Rn infinity. So the paper is by Primož Skraba and a co-author. And I mean, I think one of the main interests in that line of research was to come up with efficient algorithms for calculating persistence for such point clouds. Might have been posted a few months ago. That's okay. All.
Okay. Yeah. My second question was, if you, I mean, the fact that at the minimum enclosing radius, or just the radius of a metric space, the Rips complexes become contractible. I mean, that's easy to see, but how about the statement for the spread? Can you say what? I mean, it sounds like a much stronger result because you're relating it to a different space, and that space is only Gromov-Hausdorff close. So it sounds like a kind of interleaving argument, but then you have contractibility on the nose, and not just up to interleaving, right? And
right.
So can you say why? What's the intuition?
Yeah, first of all, notice that it's not a different space, right? It's a subset of the same space.
Okay. I thought,
So,
okay, it's actually a subset. Okay.
It is a subset. So being a subset, the idea is similar to the simplicial proof.
Okay.
Maybe that's clear, right?
Yeah.
So you have A,
then it's clear.
This creates a cone, so you can contract everything, right?
Okay, yeah. No, I thought it was an arbitrary space that's small enough and has. Okay, so then it's different. Yeah. Thanks. Okay.
One thing I can add about that is that it was interesting. You know, there's a bridge now between, say, the Riemannian approach and the simplicial approach. So Katz gave a proof for this at the level of Kuratovsky. Well, I mean, of course, he stated that as x epsilon, right? He proved that x epsilon over 2 is, and the proof was very strongly depending on analyzing certain geodesics that you have in L infinity that are not the usual straight line geodesics. But the proof at the simplicial level, we found a proof at the simplicial level, and that proof is very simple. It's very direct. So in a way, I mean, I wanted to point that out because it's a way of saying that now simplicial tools, sometimes they become much more onerous, but sometimes they actually become very, 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 very simple. So.
Further questions?
I have sort of a broad question. So you mentioned many applications of the Kuratovsky embedding. Are there like cases in which the embedding, for example, in the tight span, gives you further information? Because like by your theorem, you can embed X in any injective metric space and then thicken it there, and know the homotopy type of the Vietoris-Rips.
Yeah, thanks for the question. I can explain at least one easy consequence to motivate, say, some further conversation. But the tight span satisfies the following property. The tight span is an ambient space for X, right? So you have the tight span is the green thing, and X is this one here. As a subset of the tight span, X is within hyperbolicity of X to the tight span. So X becomes a hyperbolicity of X net for the ambient space being the tight span. Okay. So now if you look at X epsilon and you pick an epsilon larger than hyperbolicity, so that means that X epsilon is the tight span itself. So, but by, you know, the properties of the tight span is contractible. So therefore, you immediately get for free that for epsilon larger than hyperbolicity, Vietoris-Rips of 2 epsilon is contractible. And that was a direct consequence of choosing an ambient space, the ambient space E to be exactly the tight span. It's much more difficult to do this with L infinity, but with the tight span, it falls on your lap because of this property here. That is one, say, simple geometric consequence. Does that go in the direction that you wanted, Luis?
That's a great application. I mean, that's exactly the kind of thing that I have in mind.
But this one is also an application of that. The calculation can be done in the tight span and not in the whole L infinity of S1 infinity. If you had to study the epsilon thickenings of that inside of that, of course, you have an infinite dimensional space, but the fact that we know that the tight span of S1 infinity is exactly D2 makes this a geometric approach possible.
Right, right.
Yeah.
I have another question now, Facundo.
Sure.
Regarding what you just showed, or you just sketched basically in a way of proving Rips' lemma about the contractibility of the Rips complex at degree 2 delta for a delta hyperbolic space, right?
Yes.
And you could also, like, there's also extension of that if you have a subspace and that with Hausdorff distance, say R, then you get contractibility for the Rips complexes at 2 delta plus something like 4R, I think, or 6R is what you find in the book by about metric spaces with non-positive curvature.
Okay.
And I wonder, so and no, but now these the proofs I know they use the hyperbolicity definition for length spaces, so using slim triangles or something. And what you sketched somehow seems to be more metric in the sense that we don't need well, it probably applies to the notion of with Gromov products, right? So I wonder, because I always wonder whether these bounds are tight. I mean, and the reason I'm saying this is that the proof, the bounds that are in this famous book seem not to be tight. There's a 6, especially if you're interested in subspaces. And then I found some lecture notes by Hull where this has been improved to 4 times R. So the bound is 2 delta plus 4 times R. But also, I mean, it's unclear whether this is tight because he's actually proving it for another notion of hyperbolicity, not.
Who is the author?
So this is in lecture notes on hyperbolic groups by Hull.
How do you spell it? Sorry, it would be interesting.
Hull.
Okay, thank you.
Yeah. And right, if I remember correctly, this is for the for some notion of hyperbolicity that involves geodesic triangles.
Right.
Yeah.
The notion of hyperbolicity that applies in this other setting is of course one for for tuples, right? The one where you look at the excess, the defect related to not satisfying the 4-point condition. So if you have that one. And then usually the geodesic one and this one are related by a factor 2 or 3 or whatever.
So sorry, there is one comment according to this question. Even for the definition of delta hyperbolic space with 4-point Gromov products, I think it has been shown that the tight span is also delta hyperbolic. And if the space is geodesic space, as you mentioned here with geodesic triangles, the distance from the space to its tight span is equal to delta. So with delta thickening, you will get the whole injective space.
Yeah, so there's exactly. So thanks for that comment.
But first it was proven by Dress, I think, not so long. But
really?
Yeah.
So this is true. If you have X is a 3 metric space, so namely hyperbolicity of X is 0. And hyperbolicity here is defined via the 4-point condition. So then the tight span of X is a metric 3. And metric 3 means geodesic plus hyperbolicity in the same sense, 0. But the comment, I think I sorry, I don't know your name, who spoke, and I cannot see your face right now, but
Parvana.
Okay. The generalization of this is the following. So if X is geodesic, and I think now geodesic is necessary here, and hyperbolicity of X bounded by delta, then the tight span is also delta hyperbolic. right? So it's a generalization. And I think that there's a paper, the one that I know is by Lang and Schroeder. I don't remember the title, but this is an interesting claim. I don't know if they were aware of the tight span when they wrote that paper, right? When I looked at the paper, I get the impression that it was a paper written many years ago, and the language they use is not related to tight span. But then at some point, I think the construction is a construction of some universal object that I think could be characterized by being the tight span. Am I correct, Parvane?
I think that in the paper, I don't remember exactly which one of his papers is, but the rest already it tells that you don't need the geodesic condition on the metric space. For zero hyperbolicity, you get that E of x is zero hyperbolic, and he says that it can be generalized to the set of delta hyperbolicity, and I checked it and it works. But for if it is geodesic space, we have one other result that says that not only A of x is delta hyperbolic, but it is at distance delta from x.
I see.
Yeah, this one is I think that the contractibility can be obtained by this result.
Yes, exactly. So that's the one that I had here.
Yeah.
I think Luis was asking me that question. Let me see, where is it? Here. Yeah.
So if you take the delta thickening of x in A of x, then you are getting the whole A of x, and you can get the contractibility.
Right.
Yeah.
Well, thanks for the questions.
Go ahead, Ulrich.
Maybe to follow up on your last remark. I mean that also means that then with this argument, it seems that you can actually improve the bound, right? The bound from 2 delta plus to something like 2 delta plus r should be enough, right? I mean, if assuming that your argument, I mean, what you sketch is basically saying, if I'm not missing something. So what I want to get is I have a subspace at distance r, and I want to understand when the Rips complex is a subspace of a distance r of a delta hyperbolic space, and I want to understand when the Rips complexes become contractible. And then you say basically in the injective span, they become contractible at 2 delta plus r already, right?
And what are the properties of A here?
Well, yeah, not only this Hausdorff distance is known. It's a subspace and it's a distance r.
And you want to know when the Vietoris-Rips of A becomes contractible, right?
Yeah.
I see. Well, I mean, that I don't know.
Okay. Anyway,
it seems interesting, and it's related to possible generalizations of the spread as well.
Yeah, exactly. I mean, it seems to be.
Yeah. Because in the spread, in the spread case, because you assume that means that the essential idea is that the Vietoris-Rips epsilon of A is of course a subset of Vietoris-Rips epsilon of X. But this one, as soon as epsilon is larger than the spread, will become the full, the blob, right? It's contractible. Yeah. And this condition tells you that within the same bound of epsilon, you can pull it back there, right? So your question makes me think of that too, right? So that's why I asked if A satisfies anything special. But it's a little bit related, but kind of a little bit in the opposite direction.
Yeah. Okay.
Thank you. Yeah.
Facundo, I had a question if you still have time and energy, which is in your rigidity result, you say any manifolds in this class that, have sectional curvature at least one, right? And then I was curious what, you prove that, if they're, close enough in these senses, then they're spheres in a certain sense. But what are we ruling out? What manifold should I have in mind? I'm not a geometer as other manifolds that you're ruling out that they can no longer be.
So there are many, say, weird things that live there, like the CPNs, for example, or say quaternionic spaces, whatever they are. I mean, like, yeah. So there are, of course, other stuff that make that collection interesting. But some of them are so-called rank 1, I think that's the name, rank 1 symmetric spaces. And this is one example of those. Okay. So yeah, it's important. It is not, an empty class. I mean, you have things, topologically interesting things that are not spheres.
Right, like quotients of spheres by interesting subgroups. I see.
Yeah. And I mean, speaking of this, first of all, what we did is to translate the result written by Wilhelm, right? I mean, the same. We were, simply saying Wilhelm's result implies this in the context of Vietoris-Rips barcodes, and it directly implies this. There's no effort, frankly, that we had to do except simply recognize that the filling radius is an ingredient in a bar of the barcode. What I wanted to maybe ask is, suppose that now you pick 2 different manifolds in the same class. Now you have X and Y in, let me call it M, with curvature boundable by 1 and dimension N. And suppose that all barcodes agree, not just the barcode in degree N. Then can we say anything about how far away X and Y can be? So this corollary is telling us that if you happen to choose Y to be as N, then you have very little room. But it may make sense to actually think of a generalization of a question underneath this corollary, where you free both X and Y. Does that make sense?
Yeah. Thanks. Further questions? Well, thanks so much, Facundo, for the fantastic talk, and thanks everybody for the great questions and discussion afterwards.
Thanks to everyone.